Let's go through all sorts of relationships between some parameters of a second order circuit. Some of these relationships we've already seen. For example, damping factor. We are familiar with that, alpha, from looking at the time domain expressions of an RLC circuit. Remember, alpha, the damping factor, exponential damping factor, is 1 over 2 RC. But now if you use Q or Q0, you can manipulate that formula and you can obtain another formula for alpha, this time related to Q. Remember omega D, which is damped resonant frequency, or damped natural frequency, I should say. So again, you can express it using Q instead of alpha, and you can obtain that formula. I mentioned the bandwidth already, just once again. If we have this kind of behavior, not all resonant circuits behave like that. It all depends on the Q, of course. But if we have this kind of behavior, we can identify the bandwidth. So we look at the 3 dB drop on both sides, and the difference between these two frequencies is called the bandwidth. It's important to note that this is non-symmetrical, and that's how it is. Okay, those curves are never symmetrical unless you look at very, very narrow band. They're almost symmetrical, but mathematically they're never symmetrical. So this is not like a bell curve. It just usually drops much slower than it rises here. So bandwidth is just the difference between those two frequencies, as I mentioned. Half power frequency, you know what it is. It's, I think I explained why it's called half power. We have here something R times I, which is voltage divided by square root of 2. Okay, so why is it half power? Why do we call it half power? That's correct, because power is actually proportional to the square of the voltage. Okay, so when you have voltage divided by square root, you square it, you get power. Okay, or something proportional to power, and that square root becomes 1 over square root becomes 1 over 2. So that's why half power. Correct. So lots of formula here. What is important to remember, much more important than remembering all these formulae, is to actually understand what's happening, how the response look for different values of Q. But that's actually why this coefficient is called the quality factor. In not so old days, when resonant circuits were extremely often used in radio, in telecommunication, very often we wanted to have a very narrow band just to pick up one particular frequency to get rid of everything else. Okay, so then of course when you make a resonant circuit from real inductors and real capacitors, they always have some parasitics, and they can be sort of seen as a resistance in parallel with the capacitor and inductor. So when that resistance is very low in parallel circuit, okay, we have a curve. We will see that the resonance will will be very sort of wide. Okay, the resonant curve will be wider. So we say that this circuit has low quality. Okay, because normally we want it to have a very sharp resonance. That's the only reason for calling this quality factor. It could be called anything else, but because it was used to distinguish between better resonance circuits and worse resonance circuits. That's where it came from. So when the circuit is where we want the resonance circuit to have as sharp resonance as possible. So for high quality, you will observe the transfer function with a very sharp peak. When the peak is wider, then we have a low Q, and the bandwidth will be larger. Of course, not always. We not always want the bandwidth to be very small. There are some applications when we actually want the bandwidth to be large. But then that's still, we call resonance circuits with low bandwidth, high Q circuits. So there are some interesting relationships between those omegas. So omega 1 times omega 2 is equal to omega 0 squared. So omega 0 is actually equal to square root of omega 1, omega 2. How we call this expression? Anyone remembers? Anyone knows? It's a geometric mean. Okay, so omega 0 is the geometric mean of omega 1 and omega 2. For very narrow or very high quality resonance circuits, omega 1 and omega 2 are very close or almost symmetrical around omega 0. So then they omega 0 almost equals to the arithmetic mean of omega 1 and omega 2s. Okay, in another classical and pure resonance circuit is a series RLC circuit. We also looked at it briefly in one lecture. It was just one or two transparencies. I'll simply mention the circuits that exist. Okay, now look at it again. So here we have a series connection of the three components, and we apply stimulus, which is a voltage, and our response will be current. So when we do the calculations, which are actually omitted here, but are very simple, we just use impedances, which we already have. So impedance, total impedance is the sum of these impedances, R plus J omega L plus or minus 1 over minus J over omega C. So we can see that at some frequency omega R, these two components will have the same magnitude and opposite phases. They will cancel, and that frequency, strangely enough, is the same as for the parallel circuit, 1 over square root LC. We've seen that, and it's also equal to omega 0, which we are familiar with from the differential equation describing the circuit and solving that differential equation in time domain. So this is our omega 0 is our undamped resonant frequency, undamped natural frequency. Very often we swap these terms, resonant and natural frequency, because they may be the same or they may be very close. But there are circuits in which these frequencies are completely different. We also define a quality factor for a series resonance circuit. Please note here that R in this quality factor is in the denominator. So quality factor to be very large, R has to be very small. Okay, so which was the opposite in the parallel circuit. In the parallel circuit, ideal resonance circuit with infinite quality factor will have parallel resistance equal to infinity. Here, in series,